Good day, ladies and gentlemen. Last week I introduced you to another topic, difference equations, and what we did was that we tried to use the method of iterative method to solve difference equations. We got to know how to cross-check our answers, and then we investigated the dynamic stability of the solution of linear first-order difference equation. This week, I would like to, answer some of the questions that will be lingering in some of you in your minds. So why do we do all these, mathematics? What is the application in economics? So let's look at the application of difference equations in economics. So there is a small overview here. I intend using, difference equation to discuss large income determination model, the Cobweb model, and the Harrod models. Let's take the first one, the large income determination model. I think in macroeconomics, you've discussed that consumption, right, depends on CO plus, CYT minus 1, where this is autonomous consumption, C0 is autonomous consumption, C here is the marginal propensity to consume, and then Y is your income, right? Notice that aggregate demand is also equal to consumption plus investment. And we know that aggregate demand is always equal to what? Our output. And therefore, we have our output here being to our consumption, being equal to our consumption plus investment. But we know that the consumption equation can be put in the form CO plus CYT minus 1. Right? So we can comfortably do that. Look at this equation. It's a difference equation. Right? Output here for the current year is being determined based on the previous year's sort of output. Okay, so it means we have a difference equation. Now, assuming that we have investment to be constant, which is actually the case in many situations, then our equation can be reorganized in this form, and it's not very difficult to see that this is a first order linear difference equation. As we saw last week, this is the general formula of a first order linear difference equation. So this is our equation that we have over here. If we put it in this form, then we get something like this, where our B is equal to C and our A is equals what C0 plus I0. Now, once it's a first order linear difference equation, we can write this general solution, right? Am I sure? Am I right? So this is the general solution, referred to what we discussed last week or during our last lecture. It means we have this to be our general solution. As usual, there's a complementary function, and I said there's a particular, solution. Now, the MPC here is the marginal propensity to consume, which is a fraction between 0 and 1, right? And then what I intend discussing here is that will there be dynamic stability in this model? That is, if you look at what we have over here, our solution that we have over here, in the long run, as t tends to infinity, will this one tend to 0 so that we will have our equilibrium or our particular solution? The C we have over here is the marginal propensity to consume, and the marginal propensity to consume, is always a fraction, right? It's always a fraction. And therefore, what happens is that since our marginal propensity to consume is greater than 0, it's a positive number, so it means our function there will not oscillate, right? And since we have our C here, our marginal propensity consume being less than 1, right? The marginal propensity being less than 1, it means that there will be convergence. Recall, when it's less than 1, we have, let's say, our B to be equal to half, there is going to be convergence. So what it implies is that if you look at the large income determination model, as t approaches infinity, right, YT will tend to the initial value. Let me go back here and try to explain it from here. What it means is that in the long term, when there is any destabilization, what we have standing here will tend to 0, and when it tends to 0, all this additive tends to 0, and therefore our YT here will tend to our particular solution here. Right. Let me look at a very specific example. So now I have really given the consumption, equation. Investment is given, initial output is given. So we are supposed to now find the solution, check our answers, and investigate the dynamic stability. So I put it into the equation. We know our y is equal to that. We're slotting the values. We turn this into a first order, first degree difference equation. We write the solution here. And then when we simplify, we get this equation, right? You have to see that our 0.8 is greater than 0, and therefore there is not going to be any oscillation. And also we have this one to be a fraction, and therefore there is going to be a convergence in the long run. Now we want to cross-check our answers. When y is equal to 0, we get this. Y equals 1, we get this. So we take this, our initial equation, that is the equation, our initial equation, I mean this equation, right? So this is y1, this is y0, and when we put them in here, right, this is y1, we get this one, and this is the y0, and we see that they are equal. It means our solution is correct. And then when we come to the dynamic stability, this is greater than 0, there is non-oscillation. 0.8 is less than 1, and therefore we have convergence. So it means that in the long run, as t approaches infinity, the additive over here will tend to our particular solution, which is 700. I have some examples for you. Please try them. Let's look at the Cobweb model. This model more or less deals with, agricultural products. You know that if you look at agricultural products, you plan today not knowing how much, what the price is going to be, when your products are out. So your decision to more or less produce today will depend on previous year's prices, for example. And this becomes a discrete equation, right? Where your production today will depend on prices for the previous year. In certain cases, the price of the year before the previous year. So what happens is that you have your demand all right, which is our normal demand function. But what happens is that your supply, right, your supply will depend on previous years. Right, your supply will depend on previous years. So if you look at this equation here, this is your demand all right, but this is your supply, which will depend on previous year's prices. But at equilibrium, you expect the quantity demanded to be the same as the quantity supply, so you can equate them here. Right, so when we equate them and we assume that we have the same price, we can solve for this price in terms of the previous year's price. We get something like this, and this becomes a difference equation, right? So the price today is being determined by the previous year's price and this additive, right? Now, if we assume that demand and supply they are normal, then our H to be greater than 0, that's the gradient of the supply curve, but then the gradient of the demand curve should be what? Less than 0. Once we have this solution, this equation being our first order difference equation, we can straight away write the solution, which we have over here, using our usual solution that we have been, using our usual solution for a first order difference equation. This equation can be simplified into what we have over here. And if you look at what we have standard, G minus C divided by B minus H, this is equal to our equilibrium price, which we can solve from here, right? If P is equal to P, we can solve for the equilibrium price here. And therefore, we arrive, well, the demonstration is over here. So those are supply, those are demand. If we assume that price are equal, at equilibrium, then we have our equilibrium price to be equal to that. and it is the same as what we have standing here and what you have standing here. So when we insert them, we get this equation. So there's the P, the equilibrium price that we have over here, and there's the P over here. And further, we can decide to, or we do have this one as our complementary solution, and there's our particular solution. Now, the next point is to investigate for dynamic stability of this equation. Now, the dynamic stability of this equation, notice that it will depend on the ratio H divided by what? B, as usual, right? We know H is greater than 0, all right? But then B is less than 0. So this fraction is always less than B. H over B is always less than 0. So it tells you that there is going to be some oscillation, right? It means there is going to be oscillation because it's less than 0. But when we come to the convergence, we can have three situations, right? If H, the absolute value of H over B is greater than 0, then we have convergence. If it's equal to more or less -1, we have oscillating uniformly. If it's less than 1, then we have, convergence here. Sorry, here we have divergence, right? So whether it diverge, converge, will depend on the value of H and B, right? Will depend on the value of H and B. We can have an example here. We have been given the demand curve, the supply curve, initial conditions have been given, and these are the problem that we need to solve. So as usual, when you equate the demand and supply, okay, we have an equation of this nature. We write the general solution, and we get this one as the solution here. Now, cross-checking our answer, cross-checking our solution, when t is equal to 0, we get this, t equals 1, we get this. And we have this one to be our general solution, right? This one to be our initial solution, our original problem. So we have to put P1 here and P0 here and see how they behave. So P1 here and then P0 here. And then when we put in the actual values of P0 and P1, okay, we get the two to be equal, and therefore our solution is correct. And we can also find the equilibrium price. When we equate the two equations, we have the equilibrium price to be what you have over here, 500, and it's exactly what is, what is standing here as our solution here, 500 here. Now, the next point is to investigate the dynamic stability. Now, H over B here, right, is 0 minus 0.2, divided by 0.1, we get -2, which is less than 0, suggesting that the time path will oscillate, go up and down, positive, negative. Then when we look at the absolute value of H and absolute value of B, we see that we get 2 here, which is greater than 1, meaning that the time path will diverge, right? Will diverge. So it means that as t approaches infinity, the H over B raised to the power t will tend to a very large number, and therefore the time path is not dynamically stable. I have some activities for you here. Please take your time and go through, and we will look at the last model, and that is the Harrod's model, right? The Harrod's model. It's known in macroeconomics that, savings is a function of investment, it's a function of income, right? How much you save depends upon your income for that year. But then how much you invest is the difference between what you earned this year, the difference between what you earned last year, really a proportionality constant, and that determines, how much you are going to invest, right? So these equations, two equations, are well known in macroeconomics. What do we know? At the macro level, savings is equal to investment, and therefore we can put these solutions together, right? These equations, when we write them in Y, we get this, which we can simplify as what we have over here. This is a difference equation, because the current value of yt is being expressed in terms of the lag value yt minus 1. And being a difference equation, first order, linear, we can straight away write the solution. Okay, and when we use our usual formula, this is going to be, or this is the solution of our first order linear difference equation. Then the problem here is that what will happen with the stability? Okay, it all depends on a into bracket alpha minus s, right? Or alpha divided by alpha minus s. It all depends on this additive. Now, notice that we have this alpha to be greater than 1, okay? That is, the capital output ratio is always greater than 1, this one. And you know that the marginal propensity to save is also more or less a fraction. So what happens is that what we have standing here is smaller than what we have standing here. So all what we have standing here will be, greater than 1. So when you look at it, you see that this one is greater than 1. And once this one is greater than 1, it implies that the time path, will not oscillate, right? And also, we have to know that the time path will not converge, right? The time path will not converge, it will diverge as usual because it's greater than 1. And the time path will not oscillate because this value is not a negative number. So we see that, in the Harrod's model, the equilibrium is not dynamically stable. I have an example here. It's a straightforward example. As we did in the other equations, you can take time and then insert the values, reorganize them, and then you'll be able to satisfy yourself that in this model there is going to be divergence. There are some activities for you here. Please take your time and go through and make sure you do understand them. If not, please let's discuss it at the chat room. Thank you.